Okay, so for this first question, it asks us to describe the action potentials in cardiac ventricular muscle in the SA node. So I'll go ahead and start by drawing out each one of the action potentials and labeling them according to the phases and kind of describing what happens in terms of channels, ion currents, and membrane potentials. So first we'll start with the cardiomyocytes. And down here we have, this is stage 4. And this resting membrane potential is a little bit lower than ones that we've seen before. This is here at around -90. And so the gradient of potassium at this point at -90 in stage 4 is regulated by IK1. So now what we have here is phase 0, and this is the depolarization phase that is due to the influx of sodium, which is caused by the voltage-gated sodium channels. Just like the axon and skeletal muscle and other things that we've looked at before, it's the same with these heart muscles. There is a voltage-gated sodium channel that opens, which causes a depolarization and the start of the action potential due to this influx of sodium. So that is phase 0. So here at the top, we have right after this action potential reaches its peak, at the top we have phase 1 right here. And this is regulated by what are called ITO channels right here. And we have ITO1 and ITO2. And so this first one is a potassium channel, which is the transient outward channel, and this ITO2 is the chloride channel. And so this rapid repolarization happens because the sodium channels will turn off and the chloride will come into the cell, causing a rapid repolarization here in phase number 1. So here we have phase 2, and this is kind of our plateau phase of this action potential. So what happens after this rapid repolarization is we have calcium channels that open that will come into the cell, and they will kind of balance out the charge of the potassium that is leaving the cell. Because so much calcium has a 2+ positive charge, there's a good amount of positive charge coming into the cell that will offset the positive charge that is leaving the cell through potassium. So we have different representations here. We have these channels, the potassium ultra rapid, we have the potassium rapid and potassium slow channels that will increasingly cause potassium to be leaving the cell here in phase 2, which is why we have this plateau, but it'll get to a point where it will repolarize again, and that will be what we call phase 3. So here, phase 3 represents the time when the amount of potassium leaving the cell will be much greater than the calcium that is coming into the cell. So that way the overall membrane potential will go down and decrease. It will come back down to the resting membrane potential down to -90. Okay, so now we're going to talk about autorhythmic cells in the heart and their action potentials. So they differ a little bit from the other action potentials that we were looking at. So with these action potentials, there is a phase 4, a phase 0, and a phase 3. So we'll go ahead and talk about each one of those. So in phase 4, we have cells that are called funny channels, which is IF or HCN channels. And so they're called funny channels because they do the opposite of what you would think normal sodium channels do, is that when the cell depolarizes is what causes these channels to close, rather than the other way around, based on what we've learned before. So these funny channels allow for a gradual influx of sodium into the cell, which causes this depolarization and will allow us to hit threshold right here. So reaching threshold and in this phase 0 activates a voltage-gated calcium channels. We have both L-type and T-type calcium channels, and that is what these autorhythmic cells are regulated on. This action potential is caused by the activation of these voltage-gated calcium channels as opposed to sodium channels. So that is one of the ways that they are unique. And so after that happens, the influx of calcium that causes a depolarization. Here for phase 3, we will see voltage-gated potassium channels that will open. That will cause this repolarization. It will cause the membrane potential to decrease back down to around this -60 where we started. And so those are the 3 phases of the autorhythmic cells within the heart that differ a little bit from those cardiomyocytes that we talked about earlier. Okay, so now for part 2 of this question, we're going to talk a little bit about EKGs, and we're going to trace one out based on the move of the electrical gradient through the heart. So the way this is measured is here we see the positive and the negative sensors. And so EKGs don't measure the action, like individual action potentials that travel through the cells of the heart, but they measure the electric field that is caused by that depolarization of the different cells of the heart. So based on the depolarization of the cells and the charge on the outside of the cells, we will have these arrows and vectors that will determine the magnitude and the direction of the charge based on where these positive and negative sensors are located in relation to the heart. And so what we'll do is we'll just walk through each phase, and I'll go ahead and trace an EKG on this little graph here to kind of demonstrate how the electric field flows through the heart and what each wave represents on the graph. So the important principle that we're going to be using to draw this graph and to represent what we're talking about here is the importance of vectors. So here we see starting at the SA node is where everything will start from. We see all of these arrows, right, pointing out. And so what we need to do based on these arrows, we need to take the average of where all these arrows are pointing. And so if we were to draw an arrow showing the average direction, that would be here. And because it's going from this negative to a positive sensor on the graph, we'll draw a little bit of an increase, just like that, just because we're just starting out. And so as I go through, I'll change colors and show each phase in order to clearly represent what happens on an EKG. So next here in red, I've kind of shown this electrical field that has started to propagate itself through the atrium and over to the other atrium. And so this is what we see here. And on the graph, we will show more of an increase like this. As this continues and the propagation of the electric field kind of takes over both of the atria here, all the way down to here, I'll label the AV node. This will have taken over all of this space, and it will come down here, and we will label this the P wave. So next, what I've drawn here in blue is the depolarization of this septum here. And so this generalized electrical field going in this direction will cause our graph to go down and look something like this. And this is what we will call the Q wave. Okay, so after this depolarization has taken over all of this area here, the entire septum, and moving into the ventricles, we have all of these vectors showing the movement of electrical field. If we take the average, it will be going this way, down to from negative to positive, which will show this here on the graph, and this will be our R wave. after our R wave, and once everything is fully depolarized in this whole area, most of the ventricles and the septum and everything, and we have vectors going up in this direction. We see our overall vector here. Our average vector is going in the opposite direction, and so on the graph it will cause us to drop down here. And that will be called our S wave. So after the entirety of the heart has experienced that electrical field, and we've gone through the P, Q, R, and S wave, go ahead and draw here. This whole area has experienced that depolarization, but what we'll start to see is moving in the opposite direction. These average vectors will go this way, and more of this electrical field will be moving up through the heart and will be taken away like this. And once all of this depolarization electrical field goes back to normal, it will look like this. And this is called our T wave. And so that is the representation of how the electrical field moves through the heart and causes each one of these specific waves and their relation to where the electrical field is and the direction of the vectors.